Hello everyone. Now we will find frequency of oscillation, time period, and linear frequency about a stable equilibrium point in potential energy and position curve. This is type 2 problem in potential energy problems. You know that the graph for the potential energy and position for stable equilibrium is like U shape. This is your origin, this is x-axis, this is y-axis. On y-axis we take the potential energy, on x-axis we take the position. Now suppose this is the stable equilibrium point, and for it x equal to x0. You also know that for stable equilibrium point, means x equal to x0, your Vx is minimum. Right? Now we can write the Taylor expansion theorem about a stable equilibrium point between potential energy and position. It is like Vx is equal to Vx0 plus 1 upon factorial 1 del V over del x at x equal to x0, x minus x0 plus 1 upon factorial 2 del 2v over del x2 at x equal to x0, x minus x0 whole square plus 1 upon factorial 3 del 3v over del x cube at x equal to x0, x minus x0 whole cube, and so on. Now you know that at a stable equilibrium point, means at x equal to x0, your del v over del x at x equal to x0 is equal to 0. So your Taylor expansion now can be written as Vx is equal to Vx0 plus 1 upon factorial 2 del 2v over del x2 at x equal to x0, x minus x0 whole square plus, and so on. Here, because your x minus x0 is very small, so we have neglected here the higher terms. Now finally your potential energy is equal to Vx0 plus 1 by 2 del 2v over del x2 at x equal to x0 x minus x0 whole square. Let us say it is equation number 1. Now we can write it as Vx is equal to Vx0 plus 1 by 2 k x minus x0 square. This is equation number 2. Here your k is equal to del 2v over del x2. Now if you see equation number 2, it is like your spring mass like equation. So for spring mass system, you know that your angular frequency omega is equal to root k upon m. We can write omega, which is the angular frequency. It is your angular frequency and it is equal to root k upon m. That means we will write del 2v over del x2 is equal to k, and our omega is equal to root k upon m in these type of the problems. Here sometime the time period is also asked. So for time period we use the formula omega is equal to 2 pi upon t. For linear frequency we use the formula n is equal to 1 upon t. So this formula will be used for such type of the problems. Now we will solve some problems here. Your first problem is that your potential energy function is given as minus 1 by 2 ax square plus 1 by 4 bx to the power 4. Here a and b are constants and are positive. So first we will find the value of the as our earlier discussion, we find here del v over del x. So it will be equal to, we will differentiate this with respect to x, so it becomes minus 1 by 2 a into 2x plus 1 by 4 into b into 4x cube. So your del v over del x is equal to minus ax plus bx cube. When we put del v over del x equal to 0, then our relation minus ax plus bx cube becomes 0. Here it will be x minus a plus bx square equal to 0. So here one point will be x equal to 0 and the other points will be x equal to plus minus root a upon b if we solve this equation, right? So now we will find the value of del 2v over del x2. You know that your del v over del x is equal to minus ax plus bx cube. So here your del 2v over del x2 will be equal to minus a plus 3b x square. So for x equal to 0, you see that your del 2v over del x2, it will be equal to minus a, because a is positive, so it will be a negative value. That means del 2v over del x2 is negative, so it will produce unstable equilibrium point. Now for the second point, that is x equal to, we can take both as plus or minus, the result will be same. So if we take x equal to plus root a upon b, then you see here that your del 2v over del x2 will be equal to minus a plus 3b, and it will be equal to a upon b. So it becomes twice a, as a is positive, so it becomes a positive value. That means del 2v over del x2 is a positive. The point x equal to plus minus root a upon b will produce a stable equilibrium point. Now we know that del 2v over del x2 is equal to k, and here it is equal to twice a, right? So first we will calculate here the angular frequency, that will be equal to root k upon m. So your result will be twice a upon m. Now second, you have to find the time period. So for time period you will use the formula 2 pi upon omega. So it will be equal to 2 pi root, it will be m upon twice a. It can be written in per second, radian per second. It will be in second. And third, the linear frequency f can be written as 1 upon t, or sometimes we write it as n. So it will be equal to, here your relation will be 1 upon twice pi root 2a upon m per second. So we can find the value of the angular frequency, the time period, and linear frequency for such type of the problems. Now the other problems which you have to solve yourself. The second problem is that your Vx is given as a by 3 x cubed plus beta by 4 x to the power 4. Now you have to find here the angular frequency, time period, and the linear frequency. And it is given that a and beta are positive constants. Now the third problem is that Vx is equal to minus a x upon L whole square plus b x upon L to the power 4, and you have to find here again omega, t, and linear frequency. Here a, L, and b are positive constants. Now the fourth problem is VR is equal to minus A upon R plus AR0 square upon 3R cube. Here you again have to find omega, t and frequency. So in all these problems, first you will find the value of the del V over del X, then you will put del V over del X equal to 0, and from here you will find the point. So when you find the point, then you will find del 2V over del X2, and when you find del 2V over del X2, then you will calculate the value of del 2V over del X2 at the points which you have found from the putting del V over del X equal to 0. If del 2V over del X2 is positive, then it will be a stable equilibrium point. If del 2V over del X2 is negative, then it will be unstable equilibrium point. For stable equilibrium point, you can write your del 2V over del X2 is equal to K, right, where K is a constant. It is like a spring force constant. So then we use the angular frequency formula, that is equal to root K upon M. Omega is equal to root K upon M. Thank you.